Yeah. Good afternoon, everyone. I hope all of you are doing well. I am just sharing my screen. Once it is visible, please do let me know. Just give me a moment. Let me share it again. I hope all of you can able to see my screen. I guess. Fine. So, um, so we'll start something called TDSM. Today's webinar topic is on vehicle dynamics using a MATLAB. So basically, in this, we're going to understand what exactly is the vehicle dynamics was and how we can able to perform it using an MATLAB. Actually, vehicle dynamics is a very bigger topic, and MATLAB consisting of a lot of things. So we will just see a section of it, basically on the torque speed, how to get the torque speed characteristics, right, and how to store that particular data so that whenever we're going to design a motor and we can use it, right? So in that way, we're going to start our session, right? So first thing we need to understand what are the various classifications of EV simulations is been concerned, right? So if I'm talking about the classification of EV simulation, they have been divided into three types. One is the system level simulation. Second one is the unit level simulation. Third one is the component level simulation, right? So these three level of simulations are not isolated, right? In a professional automotive development engineers, if I'm talking about, they often use all three levels together. System level simulation basically tells us whether the vehicle meets its performance targets or not. Unit or subsystem level simulation will ultimately going to tell us how efficiently each major subsystem will going to work, and component level simulation will going to tell us whether individual component can survive or they can operate safely and meet the detailed design requirement, basically, right? So let us go, little brief about what exactly is system level simulation. Actually, it is an highest level of simulation, basically, because the complete EV is represented as an integrated system. It is definitely it is set of an individual unit, but all that individual unit are combined together and they ultimately create a complete system, and that's why EV is called to be as an integrated system, right? So in this system level simulation, the objective is generally to determine the overall vehicle performance, right, rather than study the detailed electromagnetic, thermal, mechanical, or semiconductor behavior of an individual component. We will see that how a system will going to behave as a whole. Right, a typical system level EV model contain a battery pack. They will contain inverters, controllers, electric motors, transmissions, reducer gears, wheels, vehicle body, driver model, road load, regenerative braking, and various vehicle control logic. Right. So instead of modeling everything which has been present inside inverter, like inverter is consisting of the transistors. So instead of designing and doing that thing, we are not doing this. We are just making a complete integration of all those system, and then we're going to study something which is nothing but called to be as a system level design, right? So hypothetical electric car having a battery pack, let us suppose 60 kilowatt hour, having a motor of, let us suppose, 150 kilowatt. Vehicle mass, it have its mass, its wheel have its own radius, it have its own reduction ratio, reduction gear ratio, it have its own drag coefficient, it have its own frontal area. So the engineer may want to determine, from 0 to 100 kilometer per hour acceleration, how the vehicle will going to behave. What is the maximum speed this vehicle can able to achieve? What is the gradability factors this vehicle can able to achieve? What kind of energy consumption is basically happening for this kind of vehicle? What must be the driving range for this particular vehicle? How the battery will vary with respect to speed, the battery SOC variation, basically. We can also able to understand motor operating regions, regenerative braking energies, even the power, battery power demands, basically, right? So system level model can simulate the entire vehicle on, drive cycles, like such as we have an WLTP drive cycles or another prescribed drive cycles, right? So for example, if a simulation predict that vehicle consume, approximately around 15 kilowatt hour per 100 kilometer, then the simplified theoretical range calculation will be 60 divided by 15 multiplied by 100 is 400 kilometers, right? So the actual range will be depend upon the usable battery energy, right? As well as it is depend upon the auxiliary loads. It will also depend upon the temperatures. It will also depend upon the driving conditions, regenerative braking, losses which is happening on the tires, even the other factors basically, right? So this is all about a system level simulations. But when we come to which is the next, which is a unit level simulation. So the second level moves one step deeper basically. Here, instead of treating the entire EV as a one integrated system, engineers isolate a specific subsystem or functional unit and study its behavior in greater detail. For example, this system includes study of battery system. This system includes study of battery thermal management system. This system include the study of inverters. This system include the study of electric motors. This system include the transmissions. This system may include the regenerative braking systems, onboard chargers, DC-DC converter, heating, ventilation, and air conditioning system, charging systems, multiple. If you wanted to design or simulate an individual unit, then that is called as a unit level simulation, right? So here in this particular level, particularly we are more focusing on efficiencies, energy economy, and subsystem optimization, right? So that is what happening in this, unit level simulation. Then we'll go to the component level simulation. This is the third level, which will go much deeper. Here, individual component are actually been analyzed with high, physically fidelity, basically, right? So depending upon engineering disciplines, they can involve the electromagnetic, they can involve the thermals, they might involve the mechanical, they might involve structural components, they might involve the semiconductors component, even they might involve the electrochemical components, even they might involve the CFD models, right? For example, we have a motor. So instead of simply modeling a motor as which is a function of current and speed, engineers may model the actual stator geometry. They may work on a rotor geometry. They may work on the selection of a permanent magnets inside a motor. They may work on the windings. They may work on the air gaps. They may work on the magnetic materials basically, and then they will calculate the quantities such as magnetic flux density, back EMF, cogging torque, ripple torque, core losses, eddy current losses, electromagnetic forces. So a tool such as finite element electromagnetic simulation can therefore provide all this detailed information that of a system level simulation never give. And that is where the component level simulations comes into actions, right? So why don't engineers use component level simulation for everything? Because we can, if we can manufacture a component very well, so we can do it. So this is one of the most important question which is very asked by the designers in case of a vehicle. Because see, computational cost will going to increase dramatically as model fidelity will going to increase. The more and more parameter you have for analyze, so the fidelity or the computational expensiveness will going to increase, right? So that is the reason why we are not always going for component level simulation. Yeah, we are going for a component level simulation. Imagine an EV, for example, you purchased an electric vehicles. Vehicles have hundreds of battery cells, several power electronic switches, multiple sensors, motor windings, mechanical components, thermal management components, control system components. Let us suppose if every physical phenomenon is modeled in complete detail, the simulation can become an extremely computationally expensive. Therefore, engineers choose an appropriate level of abstraction, and this is useful to remember its system level, unit level, and computational level, right? So basically, those who are working basically during the development stage of a motor and a controller, we usually go for a component-based simulation, right? Once that is being done, then we'll go for a unit level simulation. Once all the things is being done, everything is been classified, once they are fitted into the vehicle, there we are mostly focused on the system level simulation. We are rarely go from system level simulation to the component level simulation, right? So that is the relationship between the three, right? Fine enough. For example, let us suppose a real industry example I'm just giving you. Consider an automotive company. They are developing a new electric SUV, right? And the company has a target to achieve 0 to 100 km per hour in 8 seconds. And they might give a range of 450 km. First, the system level simulation is being done. The vehicle development team is going to create a complete vehicle model which containing battery, inverter, motor, reducer, gearbox, wheels, vehicle dynamics, drivers, road load. They test that particular thing at different combination with 120 kilowatt motor, 50 kilowatt motor, 180 kilowatt motor, 150 kilowatt motor, right? Then a company can therefore identify the suitable motor rating before building a physical prototype. Basically, once the selection of a motor is being done, then they are going to go for a component levels, basically, right? So they are go for a unit level, basically. So motor development team now investigate, for example, 150 kilowatt of motor as per designers of the vehicle had been given, which is excellent for acceleration, but increase the cost and energy consumption, right? But it is very good. So now the motor development team now investigate that 150 kilowatt motor. They are comes under the unit level simulations, right? So they create a detailed PMSM motors or a BLDC motor, whatsoever motor you wanted to use in your vehicle, and they will determine its an efficiency map. They will plot its top speed characteristics or curve. They will calculate its maximum current. They will perform a field weakening capabilities. They have their own thermal limits. The inverter team simultaneously studies switching losses, conduction losses, DC link voltage, current limits, thermal behavior, right? And the battery team are also going to investigate maximum discharge current, temperature rise, SOC windows, cell voltage limit. All those things are being properly investigated. These improved subsystem models are then fed back into the vehicle simulations, basically, right? Then we have a component level simulation, right? Now individual component are investigated. For example, motor team may use electromagnetic finite element analysis to optimize rotor magnet, even the stator windings or air gaps. And the inverter team may also investigate actual semiconductor device like MOSFETs, IGBTs, the silicon carbide, MOSFETs, switching behavior, their losses, their junction temperature. If I'm manufacturing for a battery, the battery team may investigate the cell, the electrochemical behavior of the cell, the heat generation of the cell, the degradation of the cell by studying the equivalent circuit model of a cell. So this information can use to improve the subsystem model and ultimately the complete vehicles, basically. Right. So this is a very, a core example that how in an industry they are working. So this is all types of classification as far as vehicle is been concerned, right? Right. So now if we'll go to understand that what exactly is in vehicle dynamics, why, I'm talking about what exactly do we understand the term called as, vehicle dynamics, why it is very, very important, we need to understand. So basically, if I'm talking about a vehicle dynamics, it is, we can say, a study of a vehicle response to the force, even the driver inputs, road conditions, environmental disturbances, right? So if all those things are acting onto the vehicle, they are acting like a disturbances onto the vehicle. So in an EV, it tells us that how vehicle will accelerate, how it will going to brake, how it will going to steer, how it will going to corner, how the ride will going to happen over the bumps, how the load transfer is going to happen between the tires, and how to maintain the stability. All those things are very, very important, right? So it is not studied only for the academic understanding, but in an automotive industries, vehicle dynamics is one of the, one of the foundations which is used to answer the many practical questions, basically, right? If you build this vehicle with these tires, with these suspensions, with these motors, these brake, with this battery, right? So and with this mass distribution, how will your vehicle will actually going to behave on road under multiple conditions, right? So there were major 5 reasons for understanding why it is being required. So 5 reasons of understanding that why vehicle dynamics is important. The first reason is the safety, right? Safety is probably the one of the most important reason that why we are studying the vehicle dynamics. See, a vehicle is constantly interacting with road through only 4 tire contact patches, right? So there is a road patch is being there, and tire is been getting contacted with that particular road, that is called as a contact patches, right? Almost all the force required to accelerate, brake, and turn must ultimately pass through these tires, basically. So vehicle dynamics helps engineers to understand whether the tires will maintain sufficient grip, or whether the vehicle will remain in a controllable, remain controllable during the emergency situations or not. Example, you are applying, there is an emergency braking condition. Imagine a EV is traveling at 100 km per hour and suddenly a pedestrian appears on the road. So driver applied a maximum braking. So the vehicle experiences a large longitudinal deceleration. What is longitudinal? Vehicle dynamics is divided into 3 parts. I will let you know. The vehicle will going to experience a large longitudinal deceleration. At the same time, brakes cause weight transfers. Braking will going to make the vehicle pitch shift forward. Front axle load will getting increased, rear axle load will getting decreased, and if the rear will become light and the and they can approach, the available grip limit. That is why vehicle center of gravity, wheelbase, mass distribution, brake force distribution, tire characteristics, suspension, ABS, all that matters basically, right? So vehicle dynamics engineer can simulate this before the testing is been done. So if they will simulate this before the testing, so it can be very easy for them while doing that thing. Right. Second thing is the performance, right? The second major reason is the vehicle performance. Vehicle dynamics allow engineers to determine that at 0 to 100 kilometer per hour, how the acceleration will be there, what is the maximum speed, gradability, cornering capability, braking distance, and multiple other things. For example, you had selected a motor. Suppose an EV manufacturer has two candidate motor. Motor A can able to give you 100 kilowatt of power, and motor B can able to give you 150 kilowatt of power. So it is not enough to say that 150 kilowatt is better because it has more power, right? The engineer need to determine whether the additional motor's power actually improve vehicle performance is enough to justify the additional motor mass, or the cost, the battery power requirements, even the cooling requirements, energy consumption requirement, right? So vehicle dynamic simulation can combine the motor torque speed curves, they can combine the vehicle mass, they can combine the gear ratios, they can combine the tire radius, they can also combine the road load, and they can able to predict that how the vehicle will going to accelerate. So by applying all those things, let us suppose that fine, if you are consisting of an 100 kilowatt of motor, they will give you 0 to 100 kilometer per hour in 10.2 seconds, and 150 kilowatt of motor can able to give you the same speed, same acceleration, 0 to 100 kilometer per hour in 7.8 seconds. So manufacturer can now make an engineering decision based on the quantitative result. It is not that 150 kilowatt of energy will going to 150 kilowatt of motor will going to give me 0 to 100 kilometer per hour acceleration in 7.8 seconds. So I will select that. It is depend upon multiple case studies basically, right? Right. Then definitely, if you are selecting, if you are good at vehicle dynamics, so your vehicle will feel smooth and it is not uncomfortable, right? So performance alone does not make a vehicle good. Imagine you have a two EVs, EV1 and EV2, right? So EVA is very fast acceleration, excellent cornering, but every pothole produces a strong body movement in EVA. But EV we have a slightly slower but provide an excellent ride quality. Most passenger would not want a vehicle that behave like a racing car, or on every road. There is a vertical dynamics become extremely important in that case, right? So in the potholes, if your vehicle falls, so you feel a smoother ride in that case as well. For example, if you sit in the Volvo bus and if you sit in the earlier bus, will go to Kolkata like region, there is an older bus is being running. So if you sit in a Volvo bus and you can sit in a normal buses, which is a city bus, which is not a Volvo bus basically, right? So Volvo air suspension bus for a night coach, if I'm talking about 787 bus, so that is more comfortable compared to others basically, right? Then we have something called as design optimizations, right? So vehicle dynamics is also used to optimize vehicle design before manufacturing a physical prototypes. So an automotive engineer says 100 of design variables. For example, design variables like vehicle mass, they have the wheelbase, they have the track width, center of gravity weight, height. Apart from that, they have rear end. Just give me a guys. Just give me a second. Yeah, sorry guys, sorry for the interruptions. Yeah. So yeah, where am I? I'm actually basically on the part of design optimization, right? So I told you that automotive engineers have hundreds of design variables, right? It is not only one design variables you have; they have hundred of design variables. I told you like some of them like vehicle mass, center of gravity, height, front and rear weight distribution, tire size, even the tire stiffness, even the spring stiffness, damper coefficient, steering ratios, motor torque, brake distributions, batteries locations, right? Aerodynamic coefficient, right? So changing one parameter can influence the several vehicle characteristics basically, right? So that's why vehicle dynamics will help us to optimize our vehicle every way, right? So then at the last, what we have is nothing but called to be as an just give me a moment. Yeah, predicting behavior basically, right? So what do we understand by the term called as predictive behavior? This is one of the very biggest advantages of a vehicle dynamic simulation, right? Without simulation, what will going to happen? You will once you will going to design a particular vehicle, you will going to prototype that particular vehicle, and then you will do the physical test. If any failure or if any problem happen, then again you have to redesign it basically, and you have to create a new prototype. If again it will go into some failure, you have to design a new prototype again. So that will very, very cost incur as well as time taken. So it is expensive as well as time consuming. Right. And with simulation, what will going to happen? You will going to design, you will going to convert them into the mathematical model, you will going to simulate them. Whatever the value you need to change, you can change over there, then you're going to optimize them. Once they are being optimized, all the values have been perfectly calculated, then you will going to prototype it, and then yes, 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 Rajesh. My screen is visible actually. Let me read it again, please. Is it now visible? Yeah, actually, yeah, fine. Yeah. So with simulation, what will going to happen? The number of physical iterations required is actually getting reduced, right? So that is what is an advantages of using the simulations for a vehicle dynamics, basically, right? So and in that way, we can able to predict that how our vehicle will going to behave on different conditions, right? Right. So if I'm talking about a vehicle dynamics, so our vehicle dynamics is basically been divided into three types. Whenever you are going to study any kind of vehicle dynamics anywhere, they are being basically divided into three types. One is the longitudinal vehicle dynamics, just give me a moment. Yeah, one is the vertical vehicle dynamics. Let us suppose, okay, it is not being in that way. Right, like for one is longitudinal vehicle dynamics, you can see these examples basically, right? So a longitudinal vehicle dynamics is the study of motion along a longitudinal axis whenever your vehicle is traveling in a straight axis or in the direction in which the vehicle is traveling, right? So in a normal vehicle, imagine you are drawing a straight line from the rear of the vehicle to the front of the vehicle. So that is nothing but called to be as a longitudinal axis basically. Therefore, longitudinal dynamics primarily deal with vehicle accelerations, vehicle decelerations, braking, tractions, driving force. What is the driving force required to drive that particular vehicle? Aerodynamic drag, rolling resistance, road gradient, what motor torque is required, what is the wheel torque is required, vehicle speed. So in EV, longitudinal dynamics is particularly important because of electric motor directly produces a traction torque, right? And that ultimately accelerates the particular vehicle. So for motor calculations or for the powertrain calculation, we will basically will focus on the longitudinal vehicle dynamics basically, right? Then if I'm talking about the lateral vehicle dynamics, so this is called to as a lateral vehicle dynamics, right? So lateral dynamics is a study of vehicle, motion perpendicular to its longitudinal direction, right? It is mainly associated with some kind of, turning or cornering kind of thing, right? Imagine a EV is traveling straight ahead, very, very straight, and then a driver suddenly turns its steering wheels, right? So vehicle no longer travel along its original straight path. So it's develop a lateral velocity and lateral acceleration, right? So the important parameters in this lateral dynamics is including steering angles, lateral accelerations, lateral velocities, yaw rate, even the side slip angle we are calling, cornering stiffness, tire lateral force, understeer, oversteer, vehicle stabilities. These are all is been studied under the lateral vehicle dynamics, basically, right? So what exactly makes an vehicles to turn? Because actually steering changes the orientation of the front wheel and tire generate a lateral force on the road surface, right? So this lateral tire force create a force necessary to change the direction of the motion, right? And it has been given by a famous equation F is equal to mv square upon r, where F is required lateral force, m is basically the vehicle mass, v is the vehicle speed, r is the turning radius, right? If speed increase, so force will again going to increase. That's why if we'll double the speed while maintaining the same radius of turning, the required lateral force become approximately equal to 4 times or larger than that, right? Similarly, you can go for tire slip angle. Tire slip angle is also getting calculated in lateral dynamics. Cornering is also getting calculated in lateral dynamics, basically, right? Then last part of this thing is nothing but the vertical dynamics. You can see what is vertical dynamics. It is the study of a vehicle motion on the vertical directions, right, which is perpendicular to the road surface or where the reference plane, whatever you can see. It is deal with vehicle moving up and down, and the major components which are involved in this vertical dynamics, as you can see, it is suspension, right? Springs, even the dampers, tires, vehicle bodies, road profiles, unsprung mass, sprung mass, vertical accelerations, ride comfort, suspension travels, right? So this is particularly important when the vehicle is actually travels over any kind of speed breakers, any kind of potholes, any kind of rough roads, any kind of expansion joints, any kind of uneven surface. There you can able to feel these things, right? Right. So this is what are the three dynamics which is basically been studied everywhere. Now the most important part is, do all three act together? Answer is yes. Right. In a real vehicle, longitudinal dynamics, lateral dynamics, and vertical dynamics occur simultaneously and interact with one another. Consider a real world situation. A EV is traveling at 70 km per hour and the driver applies the brake while taking a curve, while taking a turn, and the road contains a potholes, right? Now what will happen? Longitudinal motion, that means you are applying the brake, your acceleration will going to be zero or lesser than going to be zero. That's why it is called as a deceleration. If you are decelerating, then you are using the longitudinal vehicle dynamics. What is lateral? At the same time your vehicle is turning, therefore it experiences a lateral acceleration, which is a is equal to v square upon r, which is lateral vehicle dynamics. And as you have a potholes, at the same time the vehicle encountering a potholes, so suspension will going to move up and down, and therefore vehicle experiences a vertical acceleration, which is the study and part and parcel of a vertical dynamics, right? But sometimes more happen. If vehicle does not merely translate in three direction, it also rotate. This is the major, rotational motion like roll, rotation around and longitudinal axis. If the vehicle body tilt left or right, right, this is particularly noticeable during the cornering, right? So you have the roll action, you have the pitch action, you have the yaw action is being also being there, right? So based on that, your degree of freedom need to be constant. Basically, I will showcase you in the coordinate system. I will not go into that depth, but I will showcase you in the coordinate system, right? So when all the three things are actually getting combined, that is nothing but called to Besson coupled vehicle dynamics. So this is a very important professional level concept. Suppose the EV is traveling in a state and suddenly you'll apply the brake. So two kind of dynamics is actually going to happen. If potholes stop, then three kind of dynamics is actually going to happen in that case, right? So that is why you will going to study all these three things in a similar way. That is called to Besson coupled vehicle dynamics, right? So basically, these three vehicle dynamics is very depth, right? Means in case of an MTechs or people are doing the research on the vehicle dynamics as well, right? It is a very important. Even you have a smaller thing, you have a suspension design itself, you have a noise vibration kind of things in the vehicle as well, right? Electromagnetic interference, that is again somehow need to be part and parcel of an you know vehicle dynamics. Suspension design, vibrations, they are also part and parcel of a vehicle design. Steerings, right? So these we will not going to cover in today's session. We are more focused on the longitudinal vehicle dynamics, basically, right? We'll be more focused on which vehicle dynamics? We'll be more focused on the longitudinal vehicle dynamics rather than any kind of other vehicle dynamics like lateral and vertical. Will be more focused on the longitudinal vehicle dynamics, right? Because here our intention is to calculate the torque speed characteristics, or speed characteristics, how to store that value inside a MATLAB, so that while designing a motor we can able to use that torque speed value and we can able to check, basically, right? So we're going to do that using that we will have some, because longitudinal vehicle dynamics is consisting of one differential equation, and if that differential equation is then plotted in the MATLAB, we can easily able to calculate the torque speed characteristics, basically, right, of a specific vehicle, right? So in the MATLAB, we will take an actual vehicle like Maruti Suzuki Baleno, Maruti Suzuki Baleno will going to take, and we will going to see that how that will going to differ in case of that. So we will take that particular example for the purpose of our understanding, basically, right? So I hope this thing has been clear to all of you. If anyone have any doubt, you can do let me know. Yeah, no doubts anyone have. So just give me a moment. So now we'll basically going to understand on the longitudinal vehicle dynamics, basically, right? So what exactly is longitudinal vehicle dynamics? How they're going to perform. Right? Prior to that, a small introductory to the coordinate systems, basically. See, coordinate system is something basically every vehicle, actually whenever we are studying about a vehicle dynamics, coordinate system means what is exactly the coordinate means the locations of that particular vehicles, basically, right? So we have an X, Y, Z. For example, if someone will ask you in the Google map, where is the location of, let us suppose Taj Mahal, right? So what you are going to do? You are going to write Taj Mahal in the Google map, and Google map will automatically fetch you the direction for that, right? You have the Google map is also consisting of routes and all, so it will going to fetch you the direction for that, right? But actually, how the Google Map is getting the value of Taj Mahal location? He is not he don't have any picture which can able to showcase him, right? So basically, he had been understood by the help of longitude and latitude. For example, if I am also sharing my location to someone, right? So that is not I am sharing my location to the someone. I am sharing my longitude and latitude to someone. Basically, if you can able to see, there is some longitude, there is some latitude, right? Longitude are the vertical line, latitude are the horizontal line. So wherever they are going to merge and wherever you are being present, the nearest longitude and latitude is actually been showcased to you, right? And again, the maps will not going to showcase the exact position; they will showcase you the approximate positions, right? So that is what the coordinate, right? In order to get coordinate, you require two things. One is the x-axis, one is the y-axis. Where the x and y will going to meet, that particular point is nothing but the coordinate of it. You have to give x and you have to give y. Right. So likewise, the vehicle have its own vehicle coordinate system, and you have one constant global coordinate system. You can see these are the coordinate system. Generally, coordinate system have three lines basically. So you can see these are the coordinate system, and this is very important, right? This black color line, what you are watching, that is called to be as a vehicle coordinate system. Blue color line is nothing but called, sorry, this black color line is vehicle coordinate system. Blue color line is called to be as a global coordinate system. Remember, global coordinate system will nearly constant. They won't change. They will be equal for a truck. They will be equal for a bus. For them, it will be fine. But whenever I'm talking about a global coordinate system, which is being represented by black color X, Y, Z, they are the global coordinate system. You can see global coordinate system. You have an x-axis. You have this x-axis, and if you're going to move in x-axis, you will going to if you're going to move in straighter to the x-axis, you will call it as a longitudinal, right? So I told you from the rear of the vehicle, if you draw a line on the front of the vehicle, that is called as longitudinal axis. So x-axis is a longitudinal axis, and if you're going to rotate along x, it is nothing but called to be a roll. Right now, what is the y-axis? Y-axis is nothing but this axis, which is nothing but a lateral axis. And if you're going to move along this lateral axis, that is nothing but called as movement along y-axis. And if you're going to rotate along this y-axis, this is nothing but called to be a pitch motion, right? And if you move along z-axis, right? So it is nothing but called to be as a movement along z-axis, right? And if you're going to rotate along z-axis, that is nothing but called to be as a yaw, basically. Right. So in order to control the steering, you are controlling the yaw motion only, right? So steering is controlling the yaw motion, right? So this is what is nothing but called to be as an yaw, right? So yaw, you can see this is yaw, basically, right? This is a transverse pitch. It is a longitudinal direction, right? And y-axis is always called as a transverse direction axis, and z-axis called as a vertical axis. So this is called as yaw. This is called as pitch, and this is called as roll. So rotation along x is called as roll. Rotation along y is called as pitch. Rotation along z is called as yaw. So this you need to remember. Right. Okay. Then we will swiftly come to what are the various forces which is acting onto the vehicle, right? So let us suppose this basically we had started on longitudinal vehicle dynamics. Whenever the vehicle has been traveling in the straight path, whenever you wanted to find the acceleration of the vehicle, deceleration of the vehicle, braking of the vehicle, motor torque calculation, power calculation, for all that purpose, we're going to focus something called to be as a longitudinal force basically. Let us suppose your vehicle is traveling in a forward direction. So when the vehicle is traveling in a forward direction, so multiple forces coming from the opposite side to oppose your vehicle motions basically, right? So if you're going to add those all force and based on that, if we can generate higher amount of force from the vehicle internal propulsion unit, then we can able to move the vehicle, right? For example, let us suppose if I'm talking about, for example, you are moving in a frontal direction and someone is trying to stop you. If you can able to apply more force than whatever the force is applied from the front, then you can able to run your vehicle at a specific speed. So that is nothing but called to be as a longitudinal force, right? So whenever your vehicle is traveling on the forward road, so in order to get a mathematical calculations, we're going to add all the force which is opposing onto the vehicle, and then we're going to add it and we're going to equate it. What is the propulsion unit of the force? So this FTE is basically stands for force due to tractive effort, right? Tractive effort force means this force we need to generate from the vehicle only, right? From the vehicle, how much force need to be generated, that is actually been given by force due to tractive effort, right? So once we can able to calculate force due to tractive effort, then we know at what velocity this particular vehicle is moving. Then we can easily calculate the power. Power is equal to force into velocity. We can able to do. We can able to calculate the power basically, right? Even we can able to calculate the torque. We know the radius of a one wheel, right? So we can know the radius of a one wheel. So we know the force. Then we can multiply it by radius, perpendicular directions, which is radius only. Then we can easily able to calculate what is the torque is required for moving that particular vehicle. So our all fundamentals in calculating the force, because if you know this thing, we can calculate the power, we can calculate the force, or we can calculate the torque basically, right? So Ft is nothing but the tractive effort force, which is actually been comes inside the vehicle. How the tractive effort force is being generated inside the vehicle? Inside your vehicle, you have basically inside your vehicle, you have something inside your vehicle. You have something called to be as your own. Just give me a moment. Just give me a moment, please. Sorry for the interruption. There is a call for me. Just give me a moment. Give me a moment. Sorry, guys. Sorry for interruptions. Oh, sorry. It stopped presenting. Just give me sorry. Hope my screen is visible to all of you. Right? Yeah. So from where the tractive effort force is actually getting generated from the vehicle. So inside your vehicle, you have a motor, you have a battery. Battery will provide current and electricity to the motor, and the motor will going to generate the force, and using that force, the vehicle is getting torque, right? So now the question comes: what kilowatt of motor need to be installed inside a vehicle so that it can able to generate that much amount of torque, so that torque will going to generate that much amount of force that need to be calculated, right? And for that we need to calculate how much force is actually opposing the vehicle, right? So force due to T is called as a force due to tractive effort. Just give me a moment. Just give me a moment, please. Just give me a moment. Yeah, sorry guys, sorry for interruptions. Right. So basically, FTE actually stands for force due to tractive effort. Then we have an FAD, which is actually stands for aerodynamic drag force, right? Then we have an FRR, which is basically will stands for the rolling resistance force. Then we have an FLA, which is stands for a linear acceleration force. And last is nothing but called to be an F omega, which is called for an angular acceleration force. I had one thing missed in the middle, which is FHC, which is called to be an hill climbing force, basically, right? So if all this force which is at opposite to the vehicle's movement, if we're going to add all those force, then only we can able to calculate that how much how much force is actually going need to be generated from the vehicle. Based on it, our propulsion unit going to generate a power basically. Based on it, we're going to select a motor for our particular vehicle, right? So I hope this thing has been understood by you all. Right, so here it is written all those terminologies like FT is a total. It is not a total force; it's a tractive effort force basically, which has been which is the effort, which is a kind of force which is being generated by the traction unit of your vehicle. FAD is an aerodynamic drag force. FX is an hill climbing force. FLA is an linear acceleration force, and F omega is an angular acceleration force. And last one is FRR is a rolling resistance force. Right, so these all force need to be added, and whatever the combination of them, that is nothing but comes in Newton. Right, that much of force we need to apply, or greater than that force we need to apply from the motor. Then only we can able to generate a power through which our vehicle can able to propel. Right, first we're going to discuss something about an aerodynamic drag force, on what factors aerodynamic drag force is going to depend upon. Sorry. Yeah, so actually, basically, aerodynamic drag force, what exactly and how it is actually being generated. So let us suppose your vehicle is actually moving with certain velocity in a forward direction. So aerodynamic drag force tells us that every air molecules have small amount of particle consist of, right? So that small particles is giving some kind of force or giving some kind of resistance, because if that particles will going to hit the vehicle, so until they will going to have in stack or intact of the vehicle, they're going to give some kind of force to that particular vehicle, right? So that force is nothing but called as an aerodynamic drag force, because drag is nothing but if the air particles will be come over, if the air will be come over here, it will keep intact with the vehicle body, and it will take a shape of a vehicle body, and it can able to remove from the external side. Right. So this is nothing but called to as an aerodynamic drag force basically. Why? Because the air is actually getting dragged from the body. Right. Again, the aerodynamic drag force, if I'm talking about, they're segregated into two types. One is the shape drag, one is the skin drag. What is the shape drag? Shape drag is basically when depend upon the shape of the vehicle. Right. For example, you can see here is you have a vehicle, and in the front side you can see a lot of air is actually getting passed. Once all the air is actually getting passed from the here, you will going to find a higher amount of pressure which is being building over here. And whenever you are going to there, because see that air will take time in order to pass. So compared to the front side, the rear side will going to experience is a low pressure basically. So always we know the force is being passing from higher pressure to lower pressure. So in the front of the vehicle, high pressure is being created. In the back of the vehicle, low pressure is being created. So force is always acting opposite to that. So that is the reason why your vehicle is experiencing an aerodynamic drag force, right? Now that was depend upon shape of the vehicle to shape of the vehicle. For example, the truck will going to get huge amount of aerodynamic drag. The Volvo buses will going to get a lesser amount of aerodynamic drag. Why? Because Volvo buses are being designed in a way such that the air can easily pass from their body, but the trucks are being a boxy shape. So boxy vehicles, for example, if I'm talking about two vehicles, you have a Maruti Suzuki Baleno, and in that you have a Mahindra Thar. If you can take, so Mahindra Thar will have a boxing kind of shape, so their aerodynamic drag force is high compared to a Maruti Suzuki Baleno, because they are more streamlined. Right? The higher the streamline, it will the aerodynamic drag will going to less. And now the question comes: so streamlining, boxy, what are they? They are nothing but cultivation shape, and because of that shape, if something happens, if the air drag happens, that is called as a shape kind of aerodynamic drag or a shape drag. And second is the skin. Skin drag is nothing but, for example, I will just give an example. For example, you will take a sandpaper, right, and you will take a marble, right. If you're going to, slide over your marble or rub your marble or rub your finger over the marbles, and if you're going to rub your finger over the sandpaper, where you will going to feel smooth. Definitely, whenever you're going to rub your finger over the marble, you're going to feel smooth. But while you're going to rub your hand or finger over the sandpaper, you are going to feel harder, right? And that hardness feeling is nothing but going to give that hardness feeling will nothing but will going to which is happening over here as well. Because if the surface of the vehicle is not smoothened, then the air particle will take higher time to pass through, and it will ultimately create a higher drag force, basically, right? But if the smoother surface is being there, so drag force will be lesser because the air particle can easily slide past over there, right? So smoother the vehicle surface, easily the air can pass over there, and if easily can air can able to pass over there, then ultimately what I mean to say, your drag force will going to reduce, right? But if your drag force is if the skin is not smooth, other than it is many, it has many intrusions or exclusions, then ultimately your vehicle will going to experiences a huge amount of drag force, right? So based on that thing, based on the skin, that is the reason scratched vehicle will take huge amount of drag force, but normal vehicle, painted vehicle is again take a huge amount of drag force for same design. But if you change some paint to one paint to another paint, making your vehicle smooth, right, lesser scratch, that vehicle have a good skin drag. But those vehicle which is full of scratch, which have some bented part or rented parts, right, so dented parts as well, so that will again going to give you a higher skin drag, right? So I hope it is been clear to all of you this drag force. Any doubt with this, please do let me know. Any doubt with this? No doubt. Fine enough. Okay, so this is what I had been written over here, right? So now if I'm coming to the formula of an aerodynamic drag force, which is important because this is something which we're going to use in case of a MATLAB, basically. So you can see aerodynamic drag force is nothing but is equal to half rho CD AF B square, where half is a constant, rho is an air density, drag coefficient, sorry, air density of an air, right? So density of an air means it is mass. What is the mass of an air in per unit volume? That is nothing but density of an air. So density of an air is merely a constant value, right? It is something given in kg per meter cube. And again, for designing a vehicle, density of air is not common for every place. It is different. But for the designing a vehicle, we're going to take one constant value. Drag coefficient is nothing but CD, so it is a unitless, value. It don't consisting of any unit because drag coefficient is depend upon the shape of the vehicle. Whether the shape of a vehicle is a boxy, whether the shape of a vehicle is a streamline, whether the shape of a vehicle is some other kind of shape. So based on that, the drag coefficient is actually getting determined, right? So drag coefficient will based on the shape, it has been determined, right? And then you have an AF, which is called to as the frontal area of the vehicle. Definitely, frontal area of the vehicle means how much part in the front of the vehicle you can able to see. So how you will calculate a frontal area of a vehicle? You're going to multiply length, multiply by breadth. If you're going to do the length into breadth, you're going to get the frontal area of a vehicle in meter square. Then you'll have a velocity in meter per second, basically. So velocity means at what velocity the vehicle is actually traveling. So that is nothing but a velocity. So if we're going to multiply half with air density, with the drag coefficient, AF and V, the drag coefficient will be given to you. That will be depend upon vehicle to vehicle. Again, the drag coefficient has been calculated by wind tunnel testing. It has been calculated by computational fluid dynamics, CFD analysis. So it has been calculated by multiple softwares. You can easily calculate it if you have a source design of your vehicle. Right, frontal area is again getting calculated by the CFD analysis. The only thing you have to plot the value, rho is constant, half is constant, so you can get an aerodynamic drag force, basically, right? So again, air density will be depend upon multiple temperatures. It will vary at multiple heights or altitude. It will going to vary with respect to humidity. It will going to vary, right? Velocity means you can see if all the terminologies become constant for a vehicle. And for a specific place, air density, drag coefficient, and for example, you are taking a Maruti Suzuki Baleno. So your AF is constant, right? So these are all constant, which is vary, your velocity is vary. So force is directly proportional to the velocity square. If you're going to increase force, if you're going to increase velocity by 5, so force has been increased by anything. So even the small increase in velocity, you can able to increase huge amount of things basically, right? So this is all written. Basically, you can see these add-ons. They will going to increase the frontal area of the vehicle. You can see the external rear view cameras. You can see the what I mean to say, the carrier of the front, and you can see the Marshall head of the front, right? You can see the beam light, rooftop auxiliary light. This is an blind spot mirror basically, right? So you can see all these things. So these things are actually going to increase the frontal area of the vehicle, and the more the frontal area of the vehicle, the more the air getting stuck, the more the aerodynamic drag force you're going to create basically, right? So these are add-ons which are going to impact the frontal area of the vehicle, as well as it will going to impact the drag coefficient. You can see that drag coefficient for the vehicle has been given, so you can able to select any vehicle, any drag coefficient from here. For example, if you can take a two-wheeler, you can take this drag coefficient. Three-wheeler, you can take this. Open convertible vehicle, limousine, coach, truck with trailer, truck without trailer, and truck with trailer, articulated vehicle, which is having an frontal area of this much, drag coefficient of this much, you can able to. Just give me a moment, please. Right. So I hope it has been clear to all of you. Fine. So whenever you're designing a sports car, you'll always try to take a lower value of drag coefficient. Whenever you're designing a vehicle like sedans, you can take again an average value of a drag coefficient. But for SUV and trucks, drag coefficient will automatically increases because they have in larger areas of working. And for high efficiency vehicle, very high efficiency vehicles, like they will have again a lower level of drag coefficient. So you can see this boxes vehicle here, the drag coefficient is very high because they will have a larger frontal area, so CD will be very high in these cases. These are the streamlined vehicles. So here the Bugatti kind of vehicles, or Porsche. So these kind of vehicle have a lower. These are the more streamlined shaped vehicles, so they have a lesser drag coefficient, right? Now you can see the back side. This is called to be the spoilers and the splitters. So they will again going to reduce your aerodynamic drag. So these are some of the components which can able to reduce your aerodynamic drag basically. So what is happening in the splitter spoilers basically, when the vehicle is actually, what is happening, there is a two terminologies of the spoilers basically. What has happened is, because whenever there is a lightweighted vehicle and if you're trying to rotate that, you will going to trying that particular vehicle to speed at very higher speed. So some vehicle, when from the bottom you're getting a higher force, so what will going to happen, it will going to lift your rear wheels basically. That is the reason we are creating the spoilers present over here. So spoilers will going to take all those air, and instead of directly separating, they were creating a force above the spoilers, and once they will create a force above the spoiler, it will going to create a grip with this tires basically. Splitters work is not to allow any accumulations of the air in the front of the vehicle. So what they will do, they will going to split the vehicle in two parts, split the air. So in the frontal part, you won't, because if there is no splitter, the air will be come over here, it is getting junction, and slowly they will move from the front and the back. Splitter is just like a pointed tip or tooth. It can able to split the airs in two halves. One is from the bottom, one is from the top, and one from the side likewise. And ultimately your vehicle can able to cut through the air, right? So your aeroplanes, you can see the fighter planes, they have a pointed nose. They have a tendency to cut all those things basically, right? Fine. So these are what the factors, things. And again, means if you have an IC engine vehicle, naturally they will have a higher drag coefficient. Why? Because from the bottom of an IC engine vehicle, you will find a lot of Cartesians is being there, right? So these Cartesians will ultimately going to increase the drag coefficient of a vehicle, because the air will take harder time to pass through it. That is why we'll try to make the bottom of the vehicle smooth, so the air can easily pass through it. If you have the pipes and Cartesians present over here, as it is very high in case of an IC engine vehicle, because IC engine vehicle consisting of coolant pipe and as well as that, it is an supercharger or turbocharger pipes being there, your catalytic converters, all the exhaust pipe has been coming from the bottom. So the airs cannot pass as easily, basically. So that is why you can see this is an MG Gloucester, rear side. This is a rear side which has been properly covered, right? Even the aerodynamic drag will be depend upon, there is you can see the wheels are consisting of something called as this cover. These are called to be an aero covers, basically, right? So basically, if we'll place these aero covers, so what is happening? The wheels are the largest contributor of an aerodynamic drag force. Why? Because if wheels will going to rotate, they will going to accumulate all the air inside it. They won't release any air very easily, and that is the reason they are the largest contributor of an aerodynamic drag force. And that is why your wheels need to be covered with an what I mean to say, cover. So this aero cover will ultimately going to be covered your complete wheels. So very lesser amount of air will going to stored over here. But earlier wheels, which is coming like a bike, which is having the spokes, so that will going to increase the aerodynamic drag force, basically, because they will going to store the airs inside it. So they will harden to release the air from there. Right. So this is I told you about how the aerodynamic drag coefficient is been calculated. Like CD, it is not a value which has been randomly calculated or plotted. You already know what is the air density, you know the frontal area of the vehicle, you know at what vehicle you are actually rotating your wheels. So you can able to calculate the drag coefficient. So this is the velocity at which the vehicle will move. That will be calculated from the frontal air. You can see this is a tunnel, and in the tunnel you will consisting of a fans, basically. So you will know these variables. You wanted to calculate this drag coefficient, so it is can easily calculated. So this is wind tunnel testing. Sorry. This is in wind tunnel testing, right? Likewise, you have something called to as a computational fluid dynamics testing or CFD testing. You can see this is in CFD testing, which is a software-based testing through which you can able to calculate the CD, right? Then you have an own road testing with sensor, through which again you can able to calculate a drag coefficient as, right? So I hope you can able to understand what exactly is a drag coefficient, right? Yeah, definitely for go-karts also there is a drag coefficient, right? So see, for smaller kind of vehicle, because go-kart have very lesser amount of frontal areas, so you cannot feel that drag coefficient very high. But there is in the go-kart also, if you're going to design, you have to take care of the drag coefficients. So let's we move for the second thing, which is nothing but a rolling resistance, basically. So you can see this is the rolling resistance means, for example, your wheels are being there. So your wheels are in the road are being there in the wheels and the vehicle chassis. So wheels are actually getting intact with the roads, basically, right? So whatever the disturbance coming on the road, like a potholes comes, like a speed breaker comes, like a bumper comes. So all these things or vibrations is actually going into the wheels first, right? So wheels are getting deformed. It is not like wheels will be keeping them as it is. So wheels will be getting deformed. And if the wheels is getting deformed, ultimately it will going to generate some kind of resistance, and that resistance is called to be as a rolling resistance, right? Because we know wheels are nothing but called to be as made up of viscoelastic material, basically. So every viscoelastic material or elastic material, they have a property of an hysteresis loss, right? So if you're going to deform that particular rubber at giving a specific compression, while decompression, that force will be applied larger, right? So that's why during the compression, the vehicle tire will during the, because see, when you are going in front side, so this part, let us suppose this is, you are moving in this side. I'm talking about, let us suppose you are moving in this side, right? If you're moving in this side, so this part is getting compressed and this part is getting decompressed, right? So the forward part is getting compressed and the rear part is getting decompressed. So if the forward part is getting compressed, so here you can find a maximum force and here you can find a minimum force. That's why the overall force is actually going to shift to the forward side of the vehicle, right? So earlier when the vehicle is being standing, all the force is being pointed towards the center of the wheels. But when you are rotating your wheels in a forward direction, so all the forces are actually not accumulated in the center. They will be try to shift towards the more inflate or more compressed part. So they will going to force over here, right? So this is the P, which is the earlier moment of inertia, and this is the new P, which is the momentum which is shifted towards the front side. So it is the P dash, basically. So the distance covered by the P and P dash is nothing but represented by something called to be as an A A is nothing but called to be as an shift in the momentum, which is currently there at which is initially at center, and now they have been shifted to some feeders where the compression is high. So this is nothing but that A, right? So now the question comes, sir, when this compression, when this particular thing will be very high, when the tire is getting inflated. For example, inflated tire, underinflated tires. Underinflated tires means your tire will be squeezed very high from the front, right? Means underinflated tire means your tire will be squeezed very high. So in that case, your B will be shifted like this, right? So here you will have a higher A, right? You can see here you have a higher A, higher variation in terms of A is being there, right? But whenever your tire is getting overinflated, if your tire is getting overinflated, so what will going to happen? Your squeezing is very less. So if you're because if you're overinflated, so first means the compression is also very less in the forward tire. So that's why it is not getting overinflated. This is getting overinflated, and the A become less, right? So if the A become less, then something means it is not. It is very good because here you can able to roll or you can able to skid. But here basically you can able to perform in very good conditions. And again, doing operating in underinflated tires again not good. So you have to maintain a tire pressure up to certain limits, up to some 2 psi, 40-45 psi. That is depending upon the tire materials basically, right? If you have an overrated tire, then it can easily skid. And overinflated tire, if you have an underinflated tire, instead of skidding, it can generate a huge amount of aerodynamic. It can able to create a huge amount of rolling resistance force basically, right? Yeah, so you can see this is a rolling resistance force equation. FRR is equal to mu RR mg cos theta. FRR is the rolling resistance force. Mu RR is the coefficient of rolling resistance. M is a mass in kg. G is a gravitational force. Theta is a slope angle basically. Right, slope angle means at what angle the vehicle is traveling. Just wanted to showcase. Okay. You can see this. This is nothing but the slope angle, which is given by theta basically, right? So this is nothing but theta. So we have to consider that thing while calculating for a rolling resistance as well, right? Right. So whenever we are selecting a particular tire, we are always going to take a tire which is having a low rolling resistance. But again, every time taking a low rolling resistance tire will not going to impact us. Basically, rolling resistance has been calculated by this formula: P into A upon RT. P is the momentum which is there in the middle, which is given by mg. And A is nothing but X. A is nothing but that shift in the radius, basically, which is an offset distance, right? And RD is nothing but the radius of a wheels basically, which are deflated radius of the wheels, right? So if you're going to calculate this thing, so FRR is equal to P into mu RR. A upon RD is nothing but mu RR only, right? So mu RR is inversely proportional to the deflated resistance, or sorry, radius, and it is directly proportional to the offset distance basically, right? So your offset distance will be high, mu RR will be high, and your force due to rolling resistance will be very high. Right. See, whenever we are running a vehicle, we always want there should be a FRR. If there will be the nil FRR, then we can easily slip our tire in somewhere else. So it is required to just have a good FRR basically. Right. Then again, these are the multiple factors which are going to impact your rolling resistance tire, which material they are being made up of, what is the pressure inside the tire, what is the design of the tire, what kind of thread the tire is consisting of, what is the road surface, whether it is an asphalt road or whether it is an unmetallic road. In an unmetallic road, you will going to get a higher decompression. So there your resistance will be very high. At what speed you are rotating? If you're going at higher speed, then your deflation will be lesser. If you're going at lower speed, the deflation will be very high in that case, right? So again, coefficient of rolling resistance can be given in this particular standardization terms, like laboratory testing you can do a real world testing. SAE J1269, Society for Automotive Engineers, and J2452, these are also defining some of the testing technologies for rolling resistance. ISO have their own standardization basically. Right, so you can see these are the ideal rolling resistance for the vehicle: 0.007, 0.15, 0.004, 0.01, 0.02 for an off-road tires. Bicycles have this thing. Low resistance or eco-friendly tires is coming under that, right? So this is what is something. It is in fuel efficient electric vehicles as well, right? So you can see these are the multiple regions of the tires. You can see they are all dependent on, because they are all going to make your tires what is the mu RR basically, right? You can see the upper part of the tire is called as a thread area basically, which is actually comes in a contact, which you can able to see. You will go to the bottom, you can find a shoulder area basically, this yellow color zone shoulder area. And the tire is actually built upon one skeleton, right? One structure. That structure is nothing but called to be as an carcass, right? And inside that carcass, you can see these are called to be the bed area, right? Once the bed area is being damaged, actually this bed area is something which is going to keep intact or keep tight your what wheels rim basically, right? They will going to insert it into the wheels rim basically, right? And you have this side walls basically present, right? So you can see the side walls, and the tire thread have something called to BSN belts, which is been present over here, right? So if you are actually going to use a tube tire, which is now not getting used basically, so inside the tube tire you have something called to be as a tube, right? But nowadays there is no tube is been present, but they have something called to as an inner liner is being there. So tubeless tire is been coming. They are not consisting of any tube, so they are consisting of all the air basically. So inside the tube, if the tube puncture, so it is very difficult thing for the repairing. You have to properly inflate the tube. You have to do the cello. M taping. You have to do it right. Then the tube getting you can able to fill the air inside the tube. But if there is no tube, so there is no need. If you can normal seal it, right? If you can normally block it by the suction, then again the air can be easily there, right? That is why puncture repairing for tube tire will take time, but for tubeless it won't take time. But this requires skills. This tubeless tire basically, right? So if I can see in the tires, you can see this much of numbers are being written. Basically, they are being written on the sidewalls, right? So where P is first initial letter is actually representing it is a passenger vehicle, but nowadays no tires can come for P or it is not being written. Directly they have been started writing from 205. 205 is a tire width. What is the width of the tire? It is 65 is tells us the aspect ratio. Aspect ratio means what is the height of the tire sidewall as the percentage of a tire width basically, right? So now you have in this 205 is a tire width. It is given in mm. So it is 65. So 60 means 65% of 205 is nothing but the sidewall length of a tire. So it is not given directly, it is just given in percentage, right? So what sidewall height is what? It is nothing but 65% of the width of the tire, which is the 205, right? Then R represent it is a radial construction. Then another is thing there, which is the base ply construction. 15 is the rim diameter, 91 is exactly stands for the load index, which will representing what is the maximum load carrying capacity for the tire. H is representing the speed rating, that using the tire, how much speed you can able to go so that the tire can able to withstand. H is actually there that you can able to maximum achieve of 210 km/h basically, right? So likewise the tire is being written. You can see this is how the things are being written, right? So in a vehicle dynamics, we are always try to calculate the radius of the tire. So radius of the tire is never given. It is given that aspect ratio. For example, if I wanted to calculate the radius of a tire, that means I wanted to calculate this thing. I wanted to calculate this thing only, right? So actually what is been given? What is been given to us? You can see, if I can told you, what is been given? 15 is what? It is the rim diameter. Rim diameter means what is rim? You can see this white color portion is the rim. So in the bottom also it is being there. Let us suppose this rim diameter is 16. This rim diameter is 16. So what is the rim radius? Rim radius is nothing but 8, right? So only rim radius it is being there. So what is this part? This is nothing but the sidewall only. So what is the sidewall height basically? It is 55% of 195. So what is the 55% of 195? Let us calculate 55% of 195. Let me calculate in my mobile. 55 195 multiplied by 55%, you will get 107. So 107.25 plus 8, you are going to get 115.25. So 115.25 mm is nothing but called to be as an tire, the radius of that particular tire, right? So you can see this is a rim. Actually, this is given in inches. Sorry, you can have to convert them into the mm. Then you can calculate it. Sorry, I have not seen that. Actually, it is given in inches basically. So you have to convert them into the mm. Then you have to calculate this because this is already given in mm, right? Then you can calculate this thing. Basically, all the value we required in mm only, right? So this is required for the purpose of thing. Right here it was written that what this letter represent, last letter represent, what is V represent. So you can see V represent, you have U You can see we represent the vehicle can achieve the speed of 240 kilometer per hour, and what it is the maximum speed, what is the minimum speed it can able to achieve? It is 149 plus, sorry, 149 basically, right? So likewise, we have an ABCD that can able to represent the load index basically. Sorry, that can able to represent the the numbers you have that can represent the load basically. Right. So this is an hysteresis loss. So this is a contact patch where the hysteresis loss can take place. Right. This is what is called to be as a new tire, average wear tire, worn tire. But again, there's a lot of things, so we're not going to cover this. Right. So we had covered two things. One is the aerodynamic drag force and the rolling resistance force. Right. So anyone have any doubt up to this? Please do let me know. Anyone from you have any doubts up to this? What is aerodynamic drag force and rolling resistance force? I hope you can able to see that thing. Right. Fine. So let us move to some other thing, which is nothing but called to be as a hill climbing force, right? So basically, hill climbing force will only come whenever you will going to hill climbing force will only come whenever you will going to travel your vehicle in certain angles. For example, there is an angle called as theta. You will going to travel in that theta angle, then only the hill climbing force will come. Unless the hill climbing force will not going to come, and it has been given by a formula called as Fhc is equal to mg sine theta. Why sine theta? Because while traveling because every time the vector have two components. One is the cos theta component, which is a perpendicular component to the road, and one is the sine theta component, which is a parallel component to the road, right? So while taking a rolling resistance force, we are more focusing on perpendicular component. That's why there we had written mu r mg cos theta. But whenever I'm talking about the hill climbing force, so there we are not going in a perpendicular. There we are going parallel to the road. So there we are more focusing on the sine theta. So that's why there we had implemented something called to be an mg sine theta, right? So I hope this thing has been clear. So don't be confused that hill climbing force is mg sine theta. But if I'm talking about a rolling resistance force, it is mg cos theta, right? Then we have a linear acceleration. Definitely, if the vehicle moves in a straight path, so there is a linear acceleration basically. So that is called to be as an F is equal to ma, or acceleration we can write dv upon dt. So we can write m dv upon dt as well, right? Then we have force due to angular acceleration basically, because if there is a rolling resistance, so definitely there is angular acceleration comes to the vehicles, right? Which has been given upon j upon r square dv upon dt, right? So actually there is a derivation to perform all these things, but basically derivation is not a part and parcel of our webinar. I used to cover in a full-time course basically. So derivation, if you'll do, you can able to understand what factors the angular acceleration will actually going to be depend upon. We have the case study for the derivations as well, right? Material selection for the derivations too, right? So linear acceleration is m dv upon dt, and angular acceleration is j upon r square dv upon dt, where j is nothing but the moment of inertia, r is the radius of the wheel, dv upon dt is nothing but then linear acceleration only. So we can write j upon r square into a. So linear acceleration is given as change in velocity with respect to time only, right? Change in linear velocity with respect to time. Right, and angular acceleration has been given as change in angular acceleration with respect to time. And what is the relationship between linear and angular acceleration? Angular acceleration has been given upon alpha. Sorry, angular acceleration is given upon omega. So a is equal to radius into omega. So if that only we are actually calculating the things. So you can apply those normal things and you can calculate this thing, right? Fine. So if I will going to solve this thing, so. If I'm going to solve the whole equation, our equation will be look like. Actually, I don't have a pen, so I'm going to write it using there. So force due to tractive effort, if I'm talking about, if I wanted to write force due to tractive effort, it will going to calculate it as force due to angular aerodynamic drag force. So what is aerodynamic drag force? It is 1/2 half rho. Rho is nothing but we're going to get rho from where? Yeah, rho. CD we can able to get it from here. CD is a drag coefficient. CD, right? AF, that's right. AF V square. V square. Half rho CD AF V square plus force due to it is a aerodynamic drag force. Then we will come with a rolling resistance force. Rolling resistance force is mu rr mg sine theta. Just give me a moment. Put y, take a mu over here, right? So very good. Mu r mg sin cos theta, right? Plus we can write force due to angular acceleration. So you can write sorry, force due to hill driving force. We can write mg sin theta. We can write theta over here, right? Plus we can write m dv upon dt, right? M dv upon dt plus j upon r square. This is an angular acceleration basically. J upon, we can write it as r square, right? dv upon dt. Right, so this is the complete equation for a longitudinal vehicle dynamics, right? Then you can take multiple things by taking something common from here, like you can take mg common from here, so you can create one equation from here, right? And here you can take dv by dt common, and you can take other things from here, right? So for the time being, because see, whenever I told you about three things. One is system level design, one is the component level design, and a third one is the unit level design. So I'm skipping this three things: rolling resistance, right, and angular acceleration for the sake of simplicity, right? Because I don't know what is the inertia of the wheels from the, see, nobody will going to let me know what is the inertia of the wheels, right? So that's why those things which I don't know, I will going to skip it from the, means I will showcase you a MATLAB, a vehicle designing. So basically, what I will going to skip, let us suppose I'll just copy this two thing. This is the final equation basically, but while designing, I will skip these two things and then design the complete system. I will skip this angular, maybe because I don't know what is the, moment of inertia and all those things. So let me cancel that all thing. Right. So I will take this three value. Right. One is half rho CDA V square mg sin theta m dv upon dt. Right. So what I had skipped, rolling resistance I had skipped, and the angular acceleration I had skipped. See, I can even take a rolling resistance. I will let you know that how to take a rolling resistance, but for the time being, I will showcase you that how to use that particular thing. Right. So now the question comes over here. Fine, sir. What exactly this equation stands for? So basically, if I can told you about, this is called to be as a differential equation. There is some order. This is a first order differential equation. Likewise, you have a second order differential equation, right? So we know how to solve a differential equation. So let us suppose I will try to solve this particular equation. Let us suppose, right? I will try to solve this particular equation. Just give me a moment. Right? Shared a MATLAB. So just give me a moment. I am just, this is a design, predefined design which I get created. So I'm just creating a new simulation model. Yeah. I will going to solve, this differential equation from the scratch, because once you'll understand that how to create a model based on this differential equation, then you can create everything by your own, because these things, these again will not going to impact you a lot basically, right? So you need to understand that how to create that differential equations basically in case of an MATLAB has been concept, right? So if I'm talking about to go for a differential equation, let us suppose this one, right? So for that, what I need to do, I will open up the MATLAB. So I will go to the browser, right? A library browser, right? Then I will go to the Simulink. I will double click in it, and I will go to the commonly used block. I will take one constant from here. It will take bit time to come over here, right? Quick insert the block. Just give me a moment. Then I will take an integrator block from here. I can take a gain block from here, right? What else I wanted to take? I wanted to take a scope. I can take a scope from here, right? Only these things are only being required for me. Integrator, scope, and all these things. Then I will cut this thing, right? What I need to solve? I need to solve this particular equations, right? What is the equation? 5 dy by dt is equal to 6 plus this thing. So I can write the same thing likewise. Just let me copy it. I will write the same thing likewise. Control C, Control V. But instead of this thing, I can Control X and write this thing. But instead of this, we have minus, right? Sorry. Instead of this, we have minus 2 minus 6y. I can write like this. So what I will have to do, I have to first create this dy by dt block. So if I wanted to create a dy by dt block, let us suppose, yeah, I had forgot to taken one block, which is a summation block. I had taken a summation block, right? Let us suppose the output of this summation block is dy by dt, right? And if I need to multiply 5 dy by dt, let us suppose the output of this summation block is 5 dy by dt. And if I'm going to multiply it over here, I will get something called to be as 1 by 5, right? So what is the output over here? It is, just give me a moment, insert the text. Here what I get, here I will have, let us suppose 5 dy upon dt, right? Then if I'm going to pass them from the integrator block, what I will going to get dy upon dt over here, right? Right. So here I will get, sorry, here I will get 5 basically, sorry. If I'm going to integrate this thing, what I will going to get over here? I'm going to get 5y over here. What I will going to get? I will going to get 5y over here. And if I multiply, if I divide it by, what I mean to say, if I divide it by y, if I divide it by 5, so at the output of this, what I will going to get? I will get a y. I will get a y. So let us suppose y. Sorry. Sorry guys, sorry for that preference. Mistakenly. And the output of this is nothing but automation y, right?
खराब हो जाएगा ठीक है माइक्रोवेव में डालना बटन दबाना स्टार्ट का 30 सेकंड गरम हो जाएगा
So this is a 5y and this is the y basically, right? Just give me a moment. Right enough. Right. So if this thing is being there, so you can take a scope from here, right? So now what is the further solution we have to take? We have created this thing, right? We had created y as well. Now we have to multiply 6 with that. Okay, fine. Now and we have to create it on the minus side. So I will take this thing over here. I will rotate it. For rotation, I will going to use Control R, and here I will going to take 6. What I will going to take? 6. And where I have to multiply this thing, I need to multiply this thing from here, and I have to connect them to here. And I need to do it plus minus. Fine. So this is something. And now from the constant, what you are going to give? You are going to give 2 as a constant. So you can take a 2 over here. So you can place a value of 2. Right. So this is nothing but a differential equation solution, basically. This is how your differential equation is been done. So before doing that, I will have to save it. So I need to save it at somewhere. So just give me a moment. I'm using desktop, vehicle dynamics, right? Differential equation practice. So this is a basic. You have to save it by using an underscore, differential equation. So that's why I'm saving it there, right? Once I'm going to save it, it will take a bit time to save it, right? Once it will be getting saved, I'll going to, I can take it 10 seconds, right? And I will run it. Once I'll run it, it will take some time. It will give a value to me. Right, it will going to give a value to me. This is a scope. Scope is basically used for seeing the value. You can see this is the value, right? This is the plotting value which I will going to get. Right, this is a steady state value, right? So see, if I can able to solve that differential equation manually, and if I wanted to plot a graph, so I can also plot this graph only, right? But in the MATLAB, just this is actually MATLAB are 2 things, right? One, either I can write a script, or second, I can able to write something called I can able to do it using a block. So using a block, it is very, very easy to solve a differential equation, right? So this is how I can able to solve a differential equation for that, right? Similarly, you can solve it for this thing as well. You would have this particular thing for the differential equation. You can solve it, right? Likewise, you can solve it this differential equation, right? So this is a basic. It is a basic inductor resistor differential circuit, basically, right? And you can solve this particular differential equation as well, and you can able to see the current value with respect to time, how the current will going to change, right? You can see this thing. So differential equation, if you know the differential equation, and you can able to plot them inside a vehicle, basically inside a graph, not in a graph, basically in a MATLAB, so you can easily solve that particular thing, right? So that is very, very needed basically, right? Fine. So I hope it has been clear to all of you because I'm not able to see the screen. It has been clear to all of you whether you people are getting that how to means use solve the differential equations, right? Fine. So likewise, I had been solved this particular thing, right? You can see this is the Maruti Suzuki Swift Desire model, right? And this is the various thing which I had been taken for a Maruti Suzuki Swift Desire model. What I had been taken, right? As it will take some time, that's why I directly take this thing. I had taken this in the gross weight, which is being 1335 kg, right? Basically of a Maruti Suzuki Swift Desire model. Drag coefficient, I had been taken 0.35. Now I have a question, sir, whether the drag coefficient has been publicly available. I will say no, it is not available publicly. Because if they will available publicly, you can design a specific vehicle around it. Right. So they are not publicly available, but you can take it random basically. AF is been given is 2.19 meters square. A mass and density of an air is 1.127, which is constant. And AF has been calculated by multiplying the height with a width, removing the ground clearance. See, if we're going to consider the height of the vehicle, it has been calculated from the width, from the bottom of the tire, right? So from the bottom of the tire, height is not there. They have some ground clearance, right? So you have to minus that ground clearance, and then whatever the value remains, the height, you can take that. For example, just give me a moment. Let me showcase you over here. Right. For example, if this is the car of yours, let's say, just I'm designing it randomly, guys. Let us suppose this is the car, right? And in the bottom of the car, you will have something called to be as an wheels. So this is the wheels. Right. Again, you have another kind of wheels is being present, right? So these are the two wheels are being there, right? Right. So if this is a road surface, basically, if I'm talking about this is the road surface basically. This is the road surface basically, right? So if I wanted to ask you that what height has been given as far as vehicle consideration is being there, this height has been given. For the vehicle dimension, this height has been given, right? But this is not the actual frontal area. Frontal area is coming from here only. So we want to calculate this height. Which height we want to calculate? We want to calculate this height. This height I need to calculate. So for calculating this height, I need to, let us suppose this is HA and this is HB. So this is HA, right? And this is HB, right? And for calculating this height means for calculating this height, what I need to do? Let us suppose there is one height, another height is been from there. Just give me a moment. Let me create another. Sorry. Let me create this thing. This is another height basically been there, right? So this is called to be as an HC, right? So if I'm talking about HC, so if I'm talking about what is HA, HA is nothing but HB minus HC, right? HB minus HC, right? Fine. So this is nothing but HA, right? And you have a specific width of a vehicle. From the front, you have some width. If it is a 3D, so you have definitely have certain kind of width from the vehicle. Let us suppose this width, if I'm talking about. This width, right? Complete width of the vehicle, right? If I'm talking about this width, right? So this width have something. Let us suppose this width is called as WA. So I'm writing it as WA. WA, right? So what is the answer basically? So if I wanted to calculate the frontal area, right? It is nothing but HB minus HC, HB minus HC, right? Multiply by WA. Multiply by WA width. Right, so this is nothing but the frontal area of a vehicle. This is given by AF. Right, so I hope it has been clear to all of you. Fine, so this is what is called as a frontal area of a vehicle, which is a multiplication of the two heights multiplied by W. Right, this is how you can able to calculate the frontal area of a vehicle. So likewise, I'd calculate a frontal area, I'd get something called to be as in this 2.19 meters square. I've converted them into the meter because all the value has been given in mm. First I'm calculating in mm, then I will convert it to the meter square, right? Then mass density of air is merely constant. Radius is also been given. Again, the radius is not given. I had told you the formula of aspect ratio. I told you that wheel's diameter rim has been given as per the wheels. Actually, this is exact radius. I had been calculated by using a tire radius, which is the tire is being in Maruti Suzuki. I know the rim diameter. I know the aspect ratio. I can calculate the radius just in mm basic. It's just in meter. I need to calculate. First, I'll do the calculation. Then I'm going to convert them. But always remember diameter of a rim has been given in inches. So first you have to convert inches to mm. Once it has been converted inches to mm, then you can calculate the radius, right? Then you calculate using an aspect ratio the sidewall length. Once you will calculate the sidewall length, add it, right? You will get the value in mm, then you can convert them into the meter. So likewise, I will take all the values, right? You can see these values from the behind, from the back. These are nothing but called to be as an force. This is nothing but, you can see, this is the frontal area of the vehicle, this is the drag coefficient, this is the mass air density, this is half, this is 0.5, this is the velocity square, right? Now the this is nothing but mass dv upon dt, here dv upon dt. This is how the differential equation is being solved, right? This is nothing but the force I am giving. Now the question comes, sir, what force you are giving? I am not able to getting. See, the force is nothing but torque multiplied by radius, right? So this is the radius which I know, right? Torque divided by radius. Sorry, the force is nothing but torque divided by radius, and torque is nothing but force multiplied by radius, right? So if I wanted to calculate a torque, so if I wanted to calculate, if you have to apply a force, you will apply a torque, right? And that is the reason I had present over here a slider gain. Actually, what is the purpose of a slider gain? I wanted to create an torque versus speed characteristics, right? At 100 Newton meter, what is the speed? At 200 Newton meter, what is the speed? At 300 Newton meter, what is the speed? So instead of giving all the time value over here, stop the particular run and giving all the time value over here is in headache. That's why I'll create a slider gain. Instead of giving a value, I can able to reduce it or I can able to increase it by using this slider gain basically, right? In that way, I can able to create a torque speed characteristics. And you can see over here, there is an 1 upon radius and 1 upon 0.31 is been given and they have been given as an input. And this particular block is actually telling you the hill climbing force, right? You can see this is a gain which has been multiplied. So this currently, let us suppose I am taking the theta angle will be 0. So angle will be 0. So if theta angle will be 0, sine theta will be 0. So there will be no impact of this thing. If there will be some angle in between, so definitely the impact will be different, right? So let us do a small experiment to calculate it. I will going to calculate the torque speed characteristics of a particular vehicle is been concerned, right? So let us take an example at 150 Newton meter, right? So this is a complete thing. And now you have a question, sir, what this side will going to indicate? This is the conversion, right? I have to convert the speed into kilometer per hour. I have to see what is the distance covered at that particular speed. I want to see what is the wheels RPM. So that's why I have to create a wheels RPM. Okay, so here the wheels RPM will not come correct because it is in radius, actually 2 pi r. So radius has been given 0.31. So I have to take 0.31. Radius I have to take 0.31. Right? So fine. So this is nothing but something called to be as an thing, right? Now it will going to give you the wheels RPM basically, right? With no gear, right? Here we have assumed that the vehicle is not consisting of any gear because it is an EV. Now we're going to calculate, now we are eligible to calculate all these things. This is a actual mathematical model or approximate mathematical model of a vehicle is been concerned, which is a Maruti Suzuki, right? Now what I will do, I will going to save this particular model and I will run it, and I wanted to measure the torque speed characteristics of a vehicle, right? So I'm just calculating it for, let us suppose, I'm just removing it. I will calculate it from the very first. So just remove it basically. Let us suppose I'll calculate it from 5, from 0. If it is 0, speed will again become 0, right? Let us suppose if it is 10, I will calculating it for 10, right? Let us suppose I'm giving the value to 10. So let us suppose here I can put it 10, right? So I will first run it for 500 seconds to get a steady state value. If I'll run it, right? So here I will get something called to be as an, at 10, I am getting a speed of 27.53. You can just check it over here in the scope. Okay. So it is not yet steady state. It will be steady state nearly around 27.4. If I can increase it to, let us suppose 1000, you will as easily get a steady state speed. Just give me a moment. Right. Just give me a moment. you'll get a steady state speed nearly around something around 30 at something around that, right? So that is what is something is called to be as an things, right? Let us take for INF. I'll take it infinite. You can see this is a speed state. This is the actual steady state speed, actually steady state speed 31.11. Guys, just give me a moment. There is someone in the door. Just give me a moment. Guys, just give me a moment. Just give me a moment. Sorry for an interruption. Just give me a moment. This is the steady state speed. Basic steady state speed means if you're going to apply this much amount of torque, your speed will be steady at 31.11, right? So I will just calculate that particular steady state speed only. So I'll have to stop this particular iterations. Only I can able to write. Yeah, sorry for the interruptions, guys. Just give me a moment. So steady state speed will be 31.11. So this is in kilometer per hour, which I'm getting, right? I always wanted to calculate a steady state speed basically. Steady state speed means what you want, what you are getting. The speed when it is constant. If you see, if it is increasing, then you cannot say it is a steady state speed, right? If it is keep on constant, at that time my speed is become constant, right? But it is not merely constant. If you're going to change the acceleration value, then speed again drops, right? So, but I will have to plot this thing, right? Let us suppose I will calculate it for 20. So I will increase the value in the slider again up to 20. If I'll do it 20, what I'm going to get, then I will run. If I'll run, I will get a steady state speed. You can see over here, if I'll do it for this thing, I'll get 44, right? You can see the 44, right? So I need to stop these iterations. Here I will do the 44. So kilometer per hour is 44. Then let us suppose I will take it for 30. So if I do it for 30, then again I will going to run it. Here I will going to run it 30. 30. I will click it and I will run it. If I run it, I will again going to get something around 53.89. So I will stop this iteration and I will keep the plot the value over here. 53.89. 53.89, right? So sorry guys, sorry. Yeah, so now I have to increase it to 40. I will calculate it up to 50 only, right? So I will apply to 40, and if I'll run it, so I'll get 62.22 steady state speed, kilometer per hour. Means in the top you can see in a meter per second basically, right? So it is 62.22. 62 0.22. Oh, sorry. 40, it is 62.22. 62.22, right? And last, I will take it for 50. If I'll apply a torque of 50 Newton meter, what will going to happen? If I'll run it, I'll get a value of 69.57, right? So I will block it. I'll get a value of 69.57. 69.57, 69.57. I'll get this value basically, right? So this is something. Okay, so I have to plot this thing value. Okay. So this is how the speed is been calculated. See, this is the torque. If you apply 0 Newton meter of torque, it is 0. You can take it. You can take 0. You won't get anything because you have not applied anything basically. Till comes 0 only, right? Fine. So we have to stop it, right? So you can see this. This is a torque and speed basically, right? Now the question comes, whenever you're designing a motor, this torque speed characteristics is actually going to be important, right? So whenever you're designing a motor, this complete model is not required. You have to store this value at somewhere such that this value can be utilizable. And for that only, I will take you through one thing, which is 1D lookup table. Let me tell. It will take some time to get that lookup table. Just give me a moment. Yeah. So you can see there is a 1D lookup table, 2D lookup table. You can plot this 1D lookup table over here. Right now I'm cancelling it, right? So if you can click this 1D lookup table from here, you can able to create a value over here, right? So what you can do, you can see a point over it, edit table and breakpoints. You will click over here. Once you're going to click here on edit table and breakpoints, you will get one thing, right? Now you have to change the value. For example, if you're going to apply a torque of 0, means you wanted that if you're going to give the speed, what torque is been created, right? If your speed is 0, torque is 0, right? If you're going to input given 31.11, then torque will nothing but 10, right? If you're going to give 44, then torque will nothing but 20. If you're going to give 53.89, then torque is nothing but called to be as an what 53.8 is 30. If you're going to give something around 62.22, then torque is nothing but 40. If you're going to give 69.57, then torque is nothing but 50. Right? I will have to do this thing. Remaining, it is not required. Right? It is not required basically. Right? When you cannot plot it, it will fine. Right? So this is how the things will going to happen. And sorry. And then this lookup table is being saved, I hope. Lookup table has unapplied. Sorry. Try to change this. Change. Yeah, I'll get this particular value. So you can remove these values basically. From here, this value can be removed, right? Here from here, this value can be removed. Right? You can remove this value. Right? So this is a lookup table, how it has been looking like. Then you're going to click it apply and you will click it OK, right? Instead of writing those in table, you can write the value over here under a square bracket, which is the torque value, and you can write a speed value over here. And we'll click on apply. Now what is happened? The lookup value will store this particular thing. Now you have a question, sir, how do you know that lookup value store that particular thing or not? Okay, fine. I will see one thing. So let us suppose this is the torque value I am going to apply, right? And at the output, I will see on something called as a display. Okay, display is there. I will take this display to here, right? I'll remove this thing. So basically, this is the torque. This is the torque, and this is nothing but the speed. Right. So I will apply the speed and I will see what torque is coming. Right. So let us suppose I'll apply this. Let us suppose I'll apply a torque of 0. If I'll apply a torque of 0, so what will going to happen if I'll run it? Let us suppose INF, right? If I'll run it, what I'll going to get? I'll get a torque of 0, right? Let me stop it. If I'll apply a speed of 31.11, let us suppose if I'll apply a speed of 31.11, what I'll going to get? Let me see. Yeah, what I'll get torque of 10, right? If let us suppose if I'm going to apply a speed of 44, will apply a speed of 44, I was supposed to get a torque of 20. So you can see I'm getting a torque of 20. That is what is actually, yeah, I told you here I given an infinite loop. So whatever changes I have to do, I don't have to run it again and again. Whatever the changes I am going to do, that will automatically fluctuate it over here. If I'll change this value to 53.89, let us suppose 53.89. Right, so I will get something called to be as 30 Newton meter of torque. You can see whatever I had calculated it from here, it is giving us me the same. Now I have a question, sir. In this way, from 0, I will plot 5. So we had not calculated for 5. So how we can able to calculate? Let me see. If let us suppose from 0, 31.11. If my speed is 25 kilometer per hour, what must be the possible torque? Because we had not calculated over here. Let me see whether it can able to calculate or not. If I will take it for 25 kilometer per hour and if I'll apply, you can see this is the torque 8.036, which is the torque is been created. So this can able to apply the value even you had not calculate or not plotted inside a lookup table, right? Now the question comes, this is what is the speed torque characteristics of that particular lookup table, right? This is a 1D lookup table. Likewise, if you have another characteristics like you can able to calculate the speed torque value by using the theta angle. You can change this theta angle, you can change the torque, and you can able to calculate the speed value as well. Then again, it will going to find. For example, at 0 degree, this is something. At 30 degree, this is something. At 90 degree, is something. So there is a maximum gradability. It is not like that vehicle can travel 90 degree, right? It will never happen. There is some degree of angle that vehicle can easily incline. So for that particular angle, what speed is required, what torque is required, that value you can store inside a 2D lookup table basically. Now instead of complete vehicle model, we can, I'm just stopping it. Instead of using a complete vehicle model, you can use these two things and you can use these two model for the purpose of you can use this complete you can use this complete model. This I can create it as a subsystem, right? So you can use this complete model subsystem, which is an Maruti Suzuki Swift Desire, Maruti Suzuki Swift Desire, torque, speed, characteristics, right? So this is what a Maruti Suzuki Swift Desire torque, speed, characteristics. Now, while designing a motor, you don't have to take this entire model to their motor designing. You can take this torque, speed, characteristics and give the output from this particular characteristic to the input of the motors. Then based on that, you can able to draw anything, right? You can able to characterize the motor. You can able to connect 70 kilowatt of motor and you can able to see that how the motor is behaving. You can able to connect 30 kilowatt of motor and you can able to see how the motor is behaving. All those things you can able to do. Fine. So this is all about a vehicle dynamics using a MATLAB specifically, right? So I hope it has been clear to all of you. Or having any doubts? Anyone have? Oh, sorry, it is not visible. Just give me a moment. Okay, sorry, just give me a moment. Are you able to see the screen of mine? Just give me a moment because I thought this model has been skipped by you. Just give me a moment. Let me share the complete screen. That is the problem in Google Meet. I hope the MATLAB screen is visible to all of you, right? So I'm sorry, guys. Okay, I'll just quickly go through it. This is nothing but a mathematical model of a Maruti Suzuki Swift Desire, right? And you can see this is the Swift Desire, model you can able to see, right? And here you can able to calculate a torque. Means here if you're going to apply certain torque, right? Here in this particular gain, if you're going to apply certain torque, let us suppose it is 0, it is 10, it is 20, it is 30, it is 40, then you can get the value over here. This time showcasing you again. Let us suppose if I am going to apply 10 Newton meter of torque over here, applied, right? And if I'll run, So what I'm going to get? I'm getting 31.11. This is the steady state speed basically. If I click it on the scope, I'm going to fit to all point, right? You can see this is the steady speed. You can see the upper one is giving you the speed, right? Speed in kilometer per hour. This is the distance. This is the wheel speed, wheel speed in RPM. You can see this is the speed which we are achieving. This is nothing but called to be a steady state speed, which is 31.11. If you're going to apply 10 Newton meter of torque, you can get this particular thing. So you have designed this complete vehicle model, right? And if you're applying a torque, you will getting a particular speed for 20 Newton meter. You will get something around. If I'll apply 20 Newton meter, let us suppose I'll apply 20 Newton meter. If I'll apply 20 Newton meter, I'm getting something around 44. You can see I've written the things over here. For 30, for 40, for 50, you are getting some values, right? So I had started here for an infinite loop. You can take any time stamp. Basically, you can stop up 1,000. You can stop, continue up to 500. You can continue up to 2,000. Likewise, you can do anything. So I'm just stopping screen, right? Stopping the simulation value. Just I'm opening it, right? You can see there is a lookup table inside it, right? So this is called to be a 1D lookup table. How are you going to get in 1D? Actually, now the question comes, sir, we had created this torque speed characteristics, but now we have to use this torque speed characteristics whenever we are using a motor, whenever we are designing a motor, which is called this the system we are designed. Now we want to design a motor, and based on this system, we have to select a motor, and that is why the system torque speed characteristics need to be given to the motor, right? So we need to store this value at somewhere. So where we're going to store? So that is why you'll go to the library. You can create a lookup table over here, and you can get this 1D lookup table present over here. We have similarly 2D lookup table is being there. So 1D lookup table, 2D lookup table are being present. I'm just taking an example of 1D lookup table. And exported this lookup table, just doing nothing, just drag it to the workspace basically, right? Just doing nothing again, you can see, just drag it to the workspace, right? So I'm just canceling it. So whenever I'm importing the 1D lookup table over here, now if I'm clicking this 1D lookup table, double click on it, I will get the dialog boxes. So I can fill the dialog box. I can fill the torque value in the square boxes over here, 0, 10, 20, 30, 40, 50. I can able to, fill the torque like this. And I can able to fill the speed like this, right? So if I'm going to fill the torque like this, if I'm going to fill the speed like this, then I will press it apply and okay. Then this is the constant. Now you have a question, sir, corresponding to torque 10, we are giving a speed, but we are never applying a torque. We are applying the speed basically, right? So corresponding to that speed, what is the torque has been coming? Let us suppose if I wanted to calculate a torque for, let us suppose here, let us suppose if I'm applying a speed of 44, I'm getting 20 Newton meter of torque, right? Let me apply a 44 Newton meter of torque. I'm applying a 44 Newton meter of torque. Now if I'll run it, what I will get? 20 Newton meter of torque only. This is the thing which I had been applied over here. So from the vehicle model, I had extracted the value of torque speed characteristics. That value I had been plotted over here. Now the question comes, sir, in this particular thing, in this particular scenario, you had only given the formula for 44, 53.89. If I wanted to get the value between 0, if I wanted to get the speed, if I wanted to find the torque at 25 km per hour, how will I calculate? Because here there is no value 25 km per hour. Let's see whether you can calculate or not. Let me check it and we'll continue the value over here, 25. How I am fixing this value? Just double clicking over that particular block. Apply, okay. Now you can see at 25 km, I am getting this torque, right? I had never calculated for 25 km per hour. I had not calculated for 25 km per hour, but still I am getting that value. Let us suppose I am calculating it for 41 km. I have never calculated for 41. I'm calculating on 41. So if I'll apply and if I'll okay, I'll get 17.67 Newton meter. So you can see anywhere 40, I had applied for 41. No, it is 17.67 Newton meter. So that is the beauty of this lookup table. Now, you cannot use this complete model. You can use this subsystem basically for that model. Basically, I'm just stopping this thing. You can use this subsystem for the particular thing, right? So whatever the subsystem is going to get, you'll use this subsystem torque speed characteristics for the motor modeling, and then you will go to model this is a system level design, right? In motor modeling, we're going to do the component level design, and that design requires a torque speed characteristics of a system, and that torque speed characteristic of a system you can give it from here. right? So this is the basic thing. But advanced, but nowadays this is a MATLAB 2022 model. There is some vehicle dynamics block set is being also there. If I can go to the library. Yeah, you can see this is a vehicle dynamics block set. You can see the powertrain, sensor, steering system, suspension, vehicle body, vehicle scenarios, wheels, tires. This is a vehicle dynamics block set are being there. You can use this multiple vehicle dynamics block set for the purpose. You can even design a dynamic steering, kinematic steering, map steering system. Even you can design a suspension, independent double wishbone you can work on. If you are designing a suspension system and you wanted to see how your vehicle is behaving to different force from the load, you can able to take this particular suspension for that particular purpose. This is just one aspect of the thing which I had explained. There is a multiple aspect basically people are working on in the vehicle dynamics suspension things, right? Now, what exactly is a suspension? If I can show you in my PPT, I hope my PPT has been visible to all of you, right? So what exactly is a suspension? Suspension is basically which is there as a vertical kinematics. Means I told you in earlier that vertical kinetics you wanted to control it by the help of a suspension only. So suspension is something which will going to connect your vehicle chassis to the wheels basically, right? So that is what the suspension. The work of a suspension is not only to connect your vehicle chassis to the wheels, but also to absorb the shocks, but also to ensure that your tires keep on touching the ground. Also to ensure that your vehicle will be going into a controlled movement. Once if you're going to speed up your vehicle, brake the vehicle, so your vehicle is getting properly controlled that. Right. So that is why the suspensions is actually getting connected. Basically, suspension is being divided into three types. One is an independent suspension, one is an dependent suspension, and last one is nothing but called to be as a semi-independent suspension. Right. So independent suspension means this thing. You can see the movement of this tire is not impacting the movement of that tire, basically, right? So that is nothing but called to be an independent suspension, right? This is an independent suspension, right? Because the movement of one tire will not going to impact the movement of other tire, right? So that is why they are better for handling, better for riding, stability, and but they are more complex and expensive basically, right? That's why modern passenger cars are requiring a McPherson strut suspension or double wishbone kind of. You can see the MG Comet, you can see that Tata Nexon, they are all utilizing MS suspension basically, McPherson strut suspension, where you just have a one wishbone in the bottom. But whenever I am talking about double wishbone suspension, it is an expensive suspension than the McPherson strut. So they are utilizing two wishbone basically, and the shock absorber or the spring and damper system has been connected to the lower wishbone. And here the spring and damper or the strut is actually been connected to the where the strut is actually been connected to this knuckle only. You can see this knuckle only, and this is the steering link which you are going to control, and you can control the steering angle basically, right? So this is a multi-link suspension. This is basically been used in the racing cars and those which is a high efficiency cars. You're going to use a multi-link suspension. This is the most advanced suspension basically. So all this independent suspension were basically been used in the front side of the vehicle, and rear side of the vehicle is basically been utilizing the semi-independent or dependent kind of suspension, right? For example, if you wanted to carry the load, for example, if the truck is there, so truck have a rear wheels. So if you wanted to carry the load in the truck, so in the rear, you have to use a dependent type of suspension. And for that purpose only, you are utilizing this kind of suspension, which is called to as the leaf spring suspension. You can see this is the differential and this is the leaf spring. This leaf spring is consisting of the leaf plates, and the leaf plates have been connected by this particular, plates by using an U clamp, right? So once the rear wheel will going to get certain load, so this spring will going to flatten, and again they will going to come in a U shape. Right. So this is called as a leaf spring suspension, and the both means if one wheel will move, the other wheel automatically will move. They are a rigid kind of suspension, leaf spring suspension, right? But if I'm talking about a semi-independent suspension, so torsion beam, a trailing arm suspension is a semi-independent suspension. Torsion beam suspension, you can see here, this is a torsion beam suspension is an it is a kind of semi-independent suspension. In the MG Comet, you will find this suspension is being there, and in the front you have a McPherson strut suspension. This is a solid axle with leaf spring. It is again a dependent kind of suspension, right? So where you wanted to carry a heavy load, there you're going to use a dependent kind of suspension, but there the stability is being not there. That is why if you sit in the truck, stability is not there. But you will sit in the car, the stability is being there in the rear side. That's why and again, the stability is not as far as good as in the front side. In the front side, you have a higher stability. In the rear side, you have a bit less stability. That's why the rear side is utilizing a semi-independent type of suspensions, right? And if I'm talking about two-wheeler have different kind of suspensions, right? In the two-wheeler, the rear suspension is again of two type. One is monoshock suspension and one is the dual twin shock suspension. The monoshock suspension is used in the mono means the shock absorber means monoshock suspension, and dual shock suspension where the dual side have a shock absorbers, basically two shock absorbers are being there. And the front side will always been connected with the front fork telescopic suspensions, right? So this is a fork is being there, how the fork oil is being present in between, right? So they are going to absorb all the vibrations from the road, right? So this is basically you can see in the Pulsar, those vehicle who have bit higher seat, you will find this suspension, monoshock suspension. But in scooty or in black bike where you have a flattened seat, they'll have a small dual twin shock suspension like bullets, right? They can absorb huge amount of force basically, right? So this is about the suspension basically, and all this suspension are being designed. Like you can see this this is nothing but called as a swing arm. Swing arm has a specific design. The spindle connecting the swing arm has a specific design. We have to understand that how the spindle need to be taken, what is the length of this swing arm. Basically, swing arm is actually connecting your vehicle to this particular thing. This is the swing arm. Your tires has been connected to the chassis by the help of swing arm. Swing arm is need to be calculated by the formulas, right? If your swing arm length is high or low, then you can get a higher, force which is coming from the thing. So swing arm is again getting calculated by a certain technology, by MATLABs also. In a MATLABs, if we are going to design this dual suspension, you will find that swing arm length. Even in the four-wheeler also, there is swing arm is being there, right? And in this, the swing arm is actually been governed by a swing arm guard basically in your vehicle. And you have a braking system. This is again a part and partial of a vehicle dynamics basically, right? Right. So this is bit about it. Suspensions. I hope in this 2 hour session, you people had get it. So I'm done with it. If anyone have any doubt, you can please do let me know. If anyone have any doubt, please do let me know. Right. So it is actually a very bigger session, but I have somehow squeezed it in 2 hours. I know some of the concept is or is you can get it, and some of the concept you might not. Right. So anyone have any doubts, you can please do let me know. Any doubts anyone have in the MATLABs or something like that, you can do let me know. I hope you had get something from valuable information from this session. Any doubts anyone have? Thank you, sir. Thank you everyone.